All right. Well, thank you, Chris. Thank you, Lee. Welcome, everyone. Um, Here to talk to you about the love-hate relationship between moisture and concrete floor slabs. And there really is a love-hate relationship between the two. So let's first talk about the love. We love and we need moisture in a concrete floor slab. Why?
Yeah, I have
One, we need moisture to hydrate or harden the cement particles that are in the mixture.
here.
We also need water to render a concrete mixture workable, placeable, pumpable, finishable. And we need moisture or moisture retention to effectively cure a concrete or a concrete slab. Unfortunately, we have also learned to hate the very same moisture in concrete floor slabs. Why? Because moisture that's within the slab or departing from a slab can result in a vast number of very undesirable conditions. On the left, you see mold that's growing underneath a vinyl composition shingle. You can see adhesive breaking down beneath a carpet tile installation that was out in Oklahoma, slab curling, and so on and so forth. And I'm trying to move that, Chris. I can see the whole screen. That's just, is there a way to hide that? Okay, there we go. Got it. All right. One of the worst problems, and for floor covering organization, its members, its manufacturers, installers, and so on, owners as well, are the problems, the negative problems that moisture can have on floor covering and coating and so on. On the left, you're seeing delamination of a flooring system that was down in Pennsylvania. The shot in the middle is a health clinic down in Fort Lauderdale, Florida, where the adhesive is broken down, is just literally swimming. Now, when most people look at that picture, what do they say? They say the adhesive is reemulsified, but I want you to know that that is not always an accurate statement. We took water-based adhesives and coated stainless steel strips of metal. And if you do that and allow the adhesive to achieve its proper degree of set, and then you immerse that specimen, that coated strip of stainless steel metal into pH neutral water, 7 pH 7 water, neutral distilled water, it doesn't reemulsify. Okay? But you take that same specimen, you start putting it in. I'm getting some background noise from somewhere. You take that same specimen and you put it into pH solutions 10, 11, and 12, and you begin to see it slide off the metal, giving the appearance of reemulsification when it really is it's breaking down, not necessarily reemulsifying just because there's water there. So it's not always accurate to call it reemulsification. When is it reemulsification? Well, it's more often reemulsification if the adhesive never achieved its necessary degree of set in a wet set, sheet vinyl, sheet rubber, sheet linoleum installation, where the surface of the concrete is still dense and not permeable, such that the free water in the adhesive is not being readily absorbed into the surface of the concrete. What happens is everything looks great. You put the floor down, you roll it, everything looks great till they start trafficking the floor. Sometimes you start to see indents. Sometimes you see us begin to see wheel marks. In worst case scenarios, you actually can come back and you can see the arc of the notch trowel coming through the flooring because the adhesive never achieved the degree of set that it was intended to. And the bottom right picture is an epoxy floor. It's not only the coating of the flooring, floor materials or flooring industry that's experiencing problems. The polymer industry, people who manufacture, install epoxy floors, urethane floors, methyl methacrylate floors, are having very similar issues with moisture. So, because concrete loves and needs moisture, let's just take a few minutes and talk about concrete. What is it? Well, basically a composite material that is combined or comprised of four basic components. Okay, water, sand, stone, and cement. And this mixture of these four ingredients, done properly, hardens to produce a stone-like material. Pretty simple explanation. There are, however, four types of concrete. There's the concrete that you read about, hear about, and study. There's the concrete that researchers can create designers, researchers can create in the laboratory. And then there's the realcrete, which sadly sometimes can differ significantly from what the design mixture was intended to be or what we were hoping it to be. But there's another type of concrete. The fourth type is the type of concrete that nobody wants to know about, nobody wants to experience, and that's called legal crete. I am now a one-man consulting firm. I had over $80 million worth of flooring lawsuits over concrete slabs just in the last 2 years alone. $80 million worth. It's estimated that this issue is a 300 million to $1 billion issue in the United States alone. You start adding Canada and other parts of the world to it's still a very, very huge issue. Now, we need the water. We love the water because if we didn't have water, moisture in concrete, concrete wouldn't become concrete. And as I stated previously, we need it for hydration. Without moisture, water, and concrete, the cement particles wouldn't harden. Without water and concrete, we couldn't get the stuff out of the truck. It wouldn't be workable. It wouldn't be placeable. We couldn't pump it. And we certainly couldn't finish. And curing, the last thing, curing by definition is the maintenance of temperature and humidity for a specific period of time in order for the concrete to achieve its design physical properties. Okay. Now, for an example, how important curing is. This is a graph or a chart of a study, the summary of a study that was done at the Portland Cement Association in Skokie, Illinois, some years back, where they went out in the backyard and they placed 4 different concrete slabs. The line in the bottom, what they did is they placed it and did no curing whatsoever. So it was exposed to air the entire time. The next one up that you see at about the 75% level, the slab was wet cured for 3 days, then exposed to air. At the 100% 7-day level, you see they kept it wet for 7 days and then exposed it to air. And the top curve that continues to rise, they kept it wet for 180 days. And this is where, if you will, the idea of a 7-day curing period. If you properly cure concrete by one of a number of methods that we'll talk about, and retain that moisture within that slab for a period of 7 days, you will ultimately achieve 100% or close to 100% of its design physical properties, okay, without question. All right, now what are the methods that we use to cure concrete? Well, if concrete could vote, it would jump up and down to be water cured. But water curing, while a very effective method, isn't easy to do, isn't always practical, particularly on elevated slabs. And you absolutely have to avoid an alternating wetting and drying and wetting and drying. And I'm still of the opinion, because I have seen it happen, that you just cannot, when hydration takes over in the summertime, the temperature of that slab after it's finished can reach 120, 130 degrees Fahrenheit. You hit that with 55-degree water out of the ground. I've seen it craze and crack the surface of the slab. So water curing isn't always the most practical way for curing slabs that are going to be receive a floor covering or a coating system. Curing compounds. When I grew up in this business 45 years ago or more, curing compounds were the norm, particularly membrane forming curing compounds. Why? Very inexpensive, very easy to apply, accomplish the curing. However, the ASTM standard F710 standard specification, if you will, standard practice for preparing concrete subfloors to receive resilient floor coverings. Doesn't say not to use one, but it does say it's got to be removed, and it's very costly to remove. Now, there is a class of curing compounds referred to as dissipating, but they don't just break down overnight. It takes ultraviolet light, takes abrasion. It could take 60 to 90 days for it actually to break down. And as you're constructing the building and starting to frame out the floors, anywhere where there isn't significant traffic, that residue is still on the surface. So ideally, if you know ahead of time this is a floor that's going to receive a floor covering or coating, in my opinion, it's far better to consider the third class of curing methods, which are basically just moisture retaining covers. I've used dry wet strength curing paper for years. Also used in the more arid regions of the country or in the hotter, windy conditions. it's a composite material of a fabric and poly where we just wet the underside of the fabric, uh, dampen the surface. You're not continually adding water. It's a one-time thing, and it works very, very nicely. And the newer materials are lay flat. Uh, Not that it's necessarily important for a floor that's going to get covered, but if you have a bare concrete floor and you use regular poly with wrinkles and all of that, you end up with a mottled appearance, uh, if you will, negative mottled appearance on the slab, which is very undesirable, and you can't get rid of it. So these new materials are lay flat materials, if you will, not again that aesthetics are important because we're going to cover it. So yes, we love and we need moisture for every one of those reasons. Okay, we've got to have it. We need it. We've got to have it. However, after these functions have been served or performed, we've learned to hate the same water, the same moisture for a lot of reasons. One, it can lead to very serious problems with floor covering materials and coatings. And the loss of moisture from a slab can lead to volumetric changes. Only half of the water that's in a yard of concrete in that ready mix truck is necessary to harden the cement content. There is always what we call free water or water of convenience in a yard of concrete to make that concrete workable, placeable, pumpable, finishable. If you only put the amount of water that was necessary to hydrate the cement, you couldn't get the stuff out of the truck. And if you could, you couldn't do anything with it. So that free water occupies volume. And as that water is lost, begins to evaporate from the surface, a volumetric change takes place. Shrinkage, if you will, it can lead to cracking and to the warping or curling of a concrete slab. Moisture in concrete can also, if potentially reactive aggregate particles are present in the mixture, moisture can feed that process referred to as alkali silica reaction or near surface alkali reaction. These are aggregate particles that really shouldn't be in the concrete mixture, but it happens all too frequently. And we could get into explanations as why that would happen in another time. But when those potentially reactive particles exist and there's at least 85% moisture in that slab, it's like fueling the fire. And ultimately, when ASR exists, a gel forms around the coarse aggregate particles, and that gel is like it's expansive. And it can take 5 to 10 years for it to begin to crack the concrete, but it does happen. We identified a similar condition with the fine aggregate as well as coarse aggregate that was occurring in a matter of months, near surface alkali reaction, NSAR. So we got to make sure, and ready mix suppliers are supposed to do this every year. They're supposed to have their aggregate sources tested for potential reactivity. Okay, and most of them do. That's not the problem. Problem is when things get busy and you end up having to grab materials from a source that perhaps wasn't tested. Excess moisture, if you will, during finishing can result in a slab that's dusty. It can also contribute to blistering and delaminations in the slab surface. I have two schools right now down in Massachusetts where both of those schools have serious issues with delamination. I also have a 7-story hospital in Tucson, Arizona. 7 floors of lightweight concrete, all delaminated half to 3/4 inches. They've already spent $4.6 million dealing with that issue down in Tucson. So a huge issue. All right, let's take a look. Since we're doing this as a flooring organization, let's take a look at some of the common types of moisture-related floor covering and floor coating issues. The breakdown of adhesives. Okay, this is a job I did out in Oklahoma. We already talked about it not necessarily being, if you will, re-emulsification, but there was enough moisture in this concrete, if you will, to place the soluble alkalis, which are always present in the surface region of the slab, and they're always present in the surface region at a greater concentration than they are deeper in the concrete. And why is that? The natural bleeding process, when you study the specific gravity of the 4 basic components in concrete, water has a specific gravity of 1. Cement has a specific gravity of 3.15. What does that mean? That means in absolute density, cement's 3 times heavier than water. Your aggregates fall in the 2.65 to 2.85 category. Well, what does all that mean? It means when those four basic components with four different specific gravities hit the ground or hit the deck, the heavier particles are settling ever so slightly. And what happens? The lighter element, water, bleeds to the surface, but it's not pure water. That water that rises to the surface, and those of you who've placed concrete or seen it placed, you see it, bleed water, but it's not pure water. It contains any chemical, any admixture that's in the concrete or alkalis, soluble alkalis. And that's why everyone who's ever seen a test done, you always see higher levels of sodium and potassium ions in the top 3 millimeters of the concrete than you do deeper in the core. Okay. And it's those alkalis that when they go into solution that raise the pH of the concrete up to a level that can begin to attack and break down the adhesive, so on and so forth. Blistering of floor coverings and coatings. It's far more common for osmotic blisters to develop in polymer flooring than it is resilient, but they still can happen in resilient. That picture on the left is a 3/8 inch thick epoxy floor. That's the Baltimore rental car center. What kind of pressure does it take to debond 3/8 inch thick bonded epoxy flooring? People say, oh, it's vapor pressure. I said, no, it's not vapor pressure. Even at 100 degrees Fahrenheit, 100% relative humidity, vapor pressure is less than 1 psi. An osmotic cell, however, that develops in the surface region of concrete can reach 200, 300, 400, 500 psi to the point that it can actually fracture the surface region of the concrete. So both of the pictures on the far left and the bottom are osmosis occurring in polymer flooring, and what you're seeing is on the right side is osmosis that's occurred because there is an epoxy system, if you will, underneath that vinyl floor that's made to look like maple. Delamination of floor coverings. This shot here was the facility that first produced scanners for the airports after 9/11. It was a former Lucent technology facility. They tested the moisture levels were unacceptable. They bought into putting down a 2-part epoxy moisture mitigation system. They started shot blasting the floor, 200,000 square feet. So they were shot blasting 15,000 feet, move over to another 15,000, another 15,000, another 15,000. And as they moved across, then the epoxy mitigation system went down, and then a high build static dissipated epoxy went down. Well, by the time they were about 90,000 square feet across the floor shot blasting, and the first area was done, the owner or the operator of the facility was in there snapping chalk lines and getting ready to set up equipment and so forth, but brought the contractor over and said, by the way, what are all these bubbles? Time out, stop the process, start the investigation. But there wasn't time to do a proper forensic investigation. Uh, all of that existing coating that was down had to be taken up. Another system was put down. That system got the facility open, and it was so critical because if this is how serious the government was about producing these scanners. If that facility wasn't open and producing scanners by a given date, the penalty was $400,000 a day. So they put this other system down. It got the place open, built the scanners, and now you're looking at it a year later. I was amazed that we were able to peel back that big, that large a piece of high build floor coating, and you can see it's soaking wet underneath, a high pH. And the company who sold that mitigation system, who made all kinds of promises, went back across the pond. I'm not going to tell you who they are, what country they're from, but they reneged on the warranty. The first company's system failed. They stepped up to the plate and wrote a check for $600,000. And you learn a lot about who you're doing business with when you have a problem. Moisture can contribute to mold, the development of mold, which in turn can become airborne and in turn affect people's health. Very serious issue. Moisture alone can cause flooring materials to expand, delaminate. And here's a classic. This is that same picture you saw a minute ago where you see raised blisters in a sheet vinyl made to look like maple floor. What's interesting, my colleague, when we see these blisters, we typically find them to be fluid filled, okay? And what we would typically do is to puncture that blister, take a syringe, draw the liquid out, put it into glass bottles with steel caps, wrap it in aluminum foil, send it to the lab for chemical analysis. And we did that. But my colleague couldn't resist it. He said, quick, grab the camera. And we call this Old Faithful. Uh, it's not Photoshop. But the company who sold the mitigation system did something similar and used it in the lawsuit. And this is one of the very few lawsuits that became a matter of public record. 95 out of 100 lawsuits that we get involved in, myself or other firms, you end up signing or agreeing to in the settlements to non-disclosure, so we can't talk about it. This one actually became a matter of public record, was in the newspapers, yada, 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 yada. But the company who sold the mitigation system used a similar picture saying, we don't warranty for hydrostatic pressure. Well, in my deposition, when I heard that statement read to me, I said, what are they talking about? Hydrostatic. This was in Bakersfield, California, up in the mountains. Water table was several hundred feet below the surface of the facility. They didn't have 2 inches of rain the entire year. It had absolutely nothing to do with hydrostatic pressure. Uh, that company who sold that mitigation system, who installed two different systems, this floor has failed twice before it was properly corrected. They lost that lawsuit, and it became a matter of public record. Again, as it was with ASR or NSAR, there can be other things in the concrete that you as an installer inherit that you have absolutely no control over again. The shot in the middle is a school, a hospital actually I did down in Kentucky, where for this particular community, an $80 million expansion was a big deal. Today we're building $1 billion greater hospitals, but they were so proud of this. 2 weeks before the governor and the mayor were going to show up and the big ribbon cutting ceremony, they were in there spiffing up the floors, and somebody comes up and says, hey, by the way, what are all these little bumps? Stop cancel the opening, start the investigation. What it turned out was that in this concrete mixture was an unacceptably high quantity, if you will, or percentage of lignite particles. And lignite is a form of coal. They didn't do a good job of testing the moisture. When they covered the floor and the moisture redistributed and came up to the surface region, there was enough moisture to expand those lignite particles and actually cause deformity in the flooring. Another huge problem. Fortunately, the hospital hadn't opened, so it wasn't a matter of lost revenue. But again, we had to take that concrete down, remove that surface, recap it. The flooring was all down, ready to open. Huge thing. We just talked about ASR and NSAR. I'm not going to go further into that. So we hate moisture in a concrete slab because the loss of moisture, as we talked about earlier, can create a volumetric change. And volumetric change can result in drying shrinkage cracks, plastic cracks, crazing cracks, settlement cracks, negative moment cracks. Drying shrinkage, just simply the loss of moisture, if there's no provision for it, the loss of volume creates a volumetric change, and the friction of the deck or the friction of the ground, okay, can cause the concrete to crack. Now, if you had a concrete slab that you could levitate into space such that it was free to lose moisture from all six sides, there would be no internal stresses, if you will, shrinkage stresses that would result in cracking. But because we place these slabs on the ground or on deck, there's the issue of frictional restraint. Even if we're on plastic, okay, ultimately there's a measure of frictional restraint, okay, that can lead to a crack. So what do designers typically do? They typically put into the design control joints, contraction joints, saw cut typically at a given spacing. Problem with that is that if they haven't done their job and their due diligence and understanding what can happen to a moving joint or a joint that moves underneath the floor covering, it can be a real problem for a floor covering installation. Plastic cracks occur very quickly, while the concrete is still in a wet plastic state. You get a wind, hot, dry climate with wind. The moisture that's evaporating from the surface is not being replenished by the bleed water, can lead to superficial plastic cracks. There are ways to today very easily for a finisher or a GC or a project manager to know whether they're at risk. You take the air temperature, you come across to what the concrete temperature is, come down to measure your wind with this little handheld unit come across, and you can tell whether you're at risk. And there are things you can do. There are monomolecular films that you can spray it, not curing compounds, but you can spray on the surface that when minimize the plastic, the potential for plastic cracks to develop. Crazing cracks, not necessarily a defect. Very unsightly. A lot of owners panic when they see a crazed surface, but some of the best slabs that I've ever seen in my life, they've been in place for 50 years, have that type of pattern. Settlement cracks when the rebar is not properly positioned. Guys are walking on it. The concrete's beginning to set. They're walking on the rebar mat. You can get a crack over the rebar. And it's not uncommon, it's very common, if you will, for negative moment cracks to develop on elevated slabs where there's flexure in the decking itself, and you get a fixed object like a beam or a joist, you can end up with a crack over the top of the slab. But it's important, and it's important to know which type of crack you're dealing with, as I'll show you later on. Probably the biggest concern, in addition to cracking, is slab curling. Remember now, this mass of concrete that's on the ground, here it's on a vapor retarder, half of the water that's in that concrete slab is not chemically combined and is going to leave over the course of time by evaporation. And as long as that surface is open and it continues to lose moisture, volumetric change is occurring at a greater rate in the upper half of the slab than it is in the lower half of the slab. And when this happens, the edges of the slab, usually about maybe 3 to 4 feet each side of the joint, warp. Okay, and it's a huge issue. How do you know if if the slab is curled? Let's say you're doing a gymnasium. You're the flooring contractor, and you're going to put the floor down in a gym. Okay, the concrete contractor finished the concrete, and it was measured and met tolerance. You come in 6 months later, and you put a straight edge over that joint, and guess what? The joint is now the fulcrum, and that 6 foot level is teeter-tottering across that joint. Uh, you inherit that condition, and unfortunately, you had absolutely no control over it. And maybe the concrete contractor didn't have any control over it. It's a design issue in most cases. Okay, and if that isn't bad enough, there's another side of curl referred to as reverse curl. Well, what the heck is that? Reverse curl is a condition that can put the flooring material or whatever you put in to that saw cut joint into compression. You look top left, that's the MD Anderson Cancer Center down in Arizona, one of the MD Anderson Cancer Centers. And sadly, the flooring installer did not do that little test. It doesn't take much, but after they put the sheet vinyl down, the moisture gradient in the slab that led to the curling re-equalizes and reverse curl takes place. The stresses subside and it puts what's ever in the joint, whether it's a joint filler material, semi-rigid material, into compression. And you can see it in all three of these pictures where the slab sections that were curled at the joints have now gone back down and put what's in it in compression. Here's what it looks like. Okay, what's the standard treatment? More often than not, people come in, if they've checked the slab, it's curled, they grind the surface level, or in some cases they use a leveling compound. But they forget or don't consider that if the joint is raised up, there's a void underneath that slab. There's a hollow area. Again, only back several feet each side of the joint, but it's hollow. Now you come in, you put down a flooring or you put down a coating. Moisture is always attempting to seek a state of equilibrium. And as it attempts to seek that equilibrium, if you will, it redistributes. And as it redistributes, okay, up into the drier portion, the warping stresses subside, the slab sections go down because they're not being supported underneath, and it puts whatever's in that over that joint into compression. And here's the worst case where the completely buckled the underlayment and the flooring material. Same thing here. Compressible floor material in the joint. Okay, put it down, moisture redistributes, and all the joint lines telegraph through the flooring. A lot of you have seen that, may not have known it was related to the situation or the condition referred to as reverse curl. It's a great opportunity. I can show you how to stabilize a curl joint in relatively no time at all. It's a great opportunity for you to make additional money if you choose to do that. But please be aware, if you're going to put a flooring system down and you run that level across those joints, teeter-tottering, just grinding it level, or leveling it with a underlayment material isn't necessarily going to solve the problem. So it is important, absolutely critical to know how much moisture is in that slab and whether or not the level of moisture in the slab is going to increase or decrease over time, which leads us to how do we make that determination? Well, moisture testing. The tests that we perform for moisture fall into two categories: those that actually give us a number and those that basically just tell us whether it's wet or dry. On the quantitative side, historically, used for decades and decades and decades, actually goes back into the 30s and 40s in its crudest form, was the measurement of the moisture vapor emission rate by what's referred to as the calcium chloride method. In 2002, in the United States, we adopted the European method of measuring moisture in concrete floor slabs, F2170. And we also, I can't remember exactly what year we introduced the measurement, relative measurement of moisture by electrical impedance, ASTM F2659. Let's talk about the qualitative side. For years, taping down a sheet of plastic over the slab has been used, and it's still a practical method of determining if something is wet and dry. But it basically calls for taping down an 18-inch square piece of plastic, leaving it down for a minimum of 16 hours or longer, coming back, peeling back a corner, and seeing if you see a darkening of the slab or droplets of water on the underside of the plastic. If you see moisture under the plastic, do you put the floor down? Absolutely not. If you don't see moisture under the plastic, do you put the floor down? Absolutely not. So what good is it? Well, here's a test that a general contractor can perform on their own. Go out every week and put down a separate piece of plastic. And don't even think of calling anybody in to test the moisture until you stop seeing droplets or darkening. Why? It can take up to 13 pounds of emission to even show up under the plastic. So if you are seeing drops of water under the plastic, don't even think of calling in whomever is going to do the moisture testing on the project, because you're just wasting your time, wasting somebody's money at that point. All right. Still on the qualitative side, and we're actually at ASTM writing a new matte bond test where you basically, it's a mock-up, where you prepare the concrete exactly as you're going to prepare it for the full project, clean it, prep it, vacuum it, spread adhesive, put the flooring down, roll it, let it sit for usually a week, come back, and then see if an unusual amount of force is required to lift it from the subfloor. Well, unusual to who? There are ways of quantifying it that we use, but we'll see what the new standard comes up with. Let's talk about calcium chloride testing and why it's fallen out of favor. It absolutely was the norm for decades and decades and decades. But what we've learned about it has caused us to accept what I say that, quite honestly, if this is the only test you're asked to perform or the only test you do perform, the truth is it's insufficient information to base the flooring installation upon. Why? It's only telling us what's taking place in the top half to 3/4 of an inch. And this is a study that my friend Howard Kinnear and my colleague Scott Tarr performed years ago when they both were at Construction Technologies Laboratory in Illinois, where they took a 4-inch concrete slab, had humidity sensors embedded into that slab, if you will. And what they were trying to do was determine where was the moisture that you could see on top of the slab was a dish of calcium chloride pearls underneath a plastic dome. Where was the moisture that the pearls were absorbing, uh, either by emission or hygroscopic action? Where was it coming from? And what they found was that it was only the top half district. Nothing changed beyond 3/4 of an inch into that concrete. So it really amounts to conducting a calcium chloride uh, test is really the tip of the iceberg. Um, I think it's still a valuable test. Alone, it's insufficient, but as a consultant, I want as much information. If I'm asked whether it's safe to put a floor down, I want as much information as I can possibly get. Okay, but it doesn't tell the whole story. Underneath that surface is a potential reservoir, considerably greater amount of moisture that the calcium chloride test tells us absolutely nothing about. Okay, that's why we adopted the European method. Most Europeans don't use calcium chloride. Okay, they have a calcium carbide test, but relative humidity testing is the norm and has really become the norm, at least in the United States. When that concrete hits the ground, day one, it's 100% relative humidity, top to bottom. Okay, no question about it. And here we have an ambient condition of 70 degrees Fahrenheit, 50% relative humidity. So now, over the weeks and months that follow the placement of that concrete, and I want to make a point here, all of these moisture tests presume that there is an effective low permeance vapor retarder directly underneath the concrete. If it's not there, then the numbers you get are all subject to change. Okay. So with the vapor retarder in place, directly in contact with the underside of the concrete, not below sand or gravel, it's got to be directly under the concrete. Ultimately, the surface region of the slab will equilibrate with the ambient humidity, in this case 50%. But as we go deeper into the concrete, the relative humidity increases. Now you come in and you install your floor covering. And as we talked about earlier with the slab curling, what will happen is that curve, that gradient, will now reestablish itself as a state of equilibrium. But because we've lost a measure of moisture, that state of equilibrium will be at a lower RH level. So in this case, it's 80%. The research that was done at Lund University, headed up by Gordon Hedenblad, who has numerous published articles on the subject, found that where the moisture gradient and the redistribution lines intersected always fell at approximately 40% of the slab thickness. So what does that mean? It means that if you take on a 5-inch slab, 40% of 5 inches is 2 inches. You take your relative humidity test 2 inches down in a 5-inch slab, it is the predictor of what the redistribution moisture level will be once the slab is covered. So it's a great predictor of what's going to happen to the moisture level in your concrete after it's covered. Where the calcium chloride test is up testing basically the driest portion of the slab. I mean, the slab is placed. Okay, you cover cured it, you took the cover off. It's drying from the top down. Okay, the surface region of the slab is going to be the driest portion of the slab. Here, we're actually able to predict what's going to happen to that dry portion after you cover the slab. Okay. Surface pH test, and this is a real difficult thing for me to talk about because I and many of my colleagues on the ASTM committee believe that the way, as a pre-installation test, pH testing is a flawed procedure. And why is that? Simply because we're introducing an external liquid source of water that may or may not develop in the concrete itself. What is pH? It's the power of hydrogen. It basically is an indicator of acidity or alkalinity. It's a 0 to 4 or 1 to or 0 to 14 scale, really. Uh, it's not a measurement of the actual alkali content. Okay, there's a difference between pH and alkalinity. We don't have time to get into the discussion of that, but there is a difference. Okay, why test? Well, we test because there's no question that a high pH solution can break down adhesives and lead to flooring problem. No question about it. Most flooring manufacturers still require that it fall between 7 and 10. Okay, it's a measure of hydronium, hydrogen ions in solution. The point of that is if there's not enough moisture to create a solution, pH is not an issue. If I take that pH strip and put it on the top of my desk and don't add water, I have no pH at all. If I put it on a concrete slab and I don't add water, there's no pH. Okay, we talked about it being a 0 to 14 scale. Distilled water, deionized water, pH is 7, but it's a logarithmic scale. Okay, when you go from 7 to 10, you're talking a concentration difference of 1,000 times. Concrete, when it comes down the chute, is always going to test. Fresh concrete, it's going to test to 10, 12, 12 and a half, 13. What's the highest pH level? With most manufacturers, 9 to 10. So what's wrong with that picture? How can we have flooring adhesives that can only tolerate pH levels of 9, 10 going down over concrete, which, without apology, would measure fresh concrete at 12 and a half and 13? Everybody is counting on, and everybody's right, that a bare concrete surface exposed to the atmosphere will experience a degree of carbonation. Chemically speaking, CO2 reacts with moisture H2O, forms a mild form of carbonic acid, which in turn creates calcium carbonate. It lowers the pH to about 8.5 to 9. Okay, perfect. That's what we want until we come in and put down the floor covering. Okay, now we get that moisture redistribution. And if there's no vapor retarder, or if there's enough moisture still deeper in that concrete to create a solution at the surface, the alkalis go into solution. What was 8.5 or 9 now becomes 10, 11, 12, and can adversely affect the adhesive itself. And here you see some failed flooring that was removed, and you can see the salts, if you will, alkali salts underneath the surface. Pre-installation, as I warned you, okay, we are actually, I believe, very close at ASTM to removing the requirement in ASTM F710. We're going to move it, a discussion of pre-installation pH testing to the appendices. Okay, they may ultimately develop a test procedure. As a forensic tool, it's invaluable. When I go on a floor covering failure and I lift up the flooring and there's fluid and you conduct a pH test, it tells you what the adhesive is actually experiencing. Invaluable. Okay, please don't get the idea that I'm saying pH testing isn't valuable. I'm saying that as a pre-installation procedure, it's flawed in the sense that we're introducing an external source of liquid water that may or may not actually develop. So we, okay, we're working on a new procedure that simulates what's going to happen, and that ultimately will hopefully be developed to the point that we can talk about pre-installation pH testing. But be warned, valuable tool for forensic investigations. pH, no question. High pH solutions can break down water-based adhesives, can actually attack any type of adhesive over a longer period of time. So will the love-hate relationship between moisture and concrete slabs, will it end anytime soon? I don't think so. Probably not. But by having a better understanding of the relationship between the two and how to deal with it, it just may help all of us keep from having to learn about that fourth type of concrete, legal creep. All right, Chris, you want to bring us back to the questions?
Terrific. Great information, Peter, as usual. Thank you so much.